So this is a screencast addressing the standard. I can either discuss the origin of Ampere's law or calculate the magnetic field for a symmetric situation. So I just decided to talk about a solenoid since it was easy enough, and so I tried to be careful about drawing it, but I said that there was a loop density of 3 loops per meter and that there's a current running through the situation of 3.5 amps, and so it would be coming out, the fields are going this way. This is what we're expecting. It's net this way. And I was looking at 2 Amperian loops, one outside of the solenoid and one inside the solenoid, or having one component of it. So first off, the one outside the solenoid, as this side goes to infinity, it's going to be equal to 0. These two are perpendicular to it, so the dot product, which is I dot dl, that's going to be 0. And this one is also going to be equal to 0 because this is 0 because there's no current poking through this area here. So this whole thing is 0 because it's not. That's what I remember in lab, is there was nothing outside the solenoid. But on the inside of the solenoid, we have the. I watched your screencast, so it's just B. It eventually simplifies to B is equal to the loop density times mu naught times the current, and which is easy enough because that's just 5 loops per meter times 4 pi times 10 to the negative 7th, I think. Yeah, 10 to the negative 7th times 3.5 amps, which is 2.199 times 10 to the negative 5th Teslas. And that's, again, directed this way. Yeah. If we were to have a similar situation, except for it was a toroid, like a donut, we would also have the same thing where it would be 0 inside the toroid and 0 outside the toroid, but inside of like the loops, that's where we'd have a B field that would be have to do with which way we want the right-hand rule would tell us in which direction.